Hello, everyone. My name's Jamie Angus Whiteoak. I'm actually the VP for Northern Europe, but it's my pleasure to chair this session for the UK section, where we're going to have Mike Turner talk to us about the transformer, which actually is a very important component that's often forgotten. Let me tell you a bit about Michael, or Mike as we call him. Mike began his engineering career in 1985 with the BBC in London, and then branched out into industrial electronics, developing servo motors, power electronics, and control systems at the University of Leeds spin-out company called SR Drive Limited, where the need to quieten noisy electric motors also led to study of vibration, sound radiation, and basic acoustics. However, he had a lifelong interest in audio electronics and sound recording, and realized that his experience of motor design, feedback control systems, and dynamics were actually transferable to loudspeakers. And I met him when he was doing a part-time PhD in voice coil motor control, and later the development of a patented control and linearization scheme for moving coil drive units, which I believe is incorporated into some of the KEF products that we're seeing arrive on the market recently. Since 2019, Mike has actually been independent and operated his own consulting and technology licensing business, Active Transducer Research Ltd, which, as well as the active loudspeaker work, also offers diverse expertise in analog and power electronics, motor control, system design analysis, and Class D amplification. Mike's been an AS member since 2003 and describes the AS as having played an invaluable, indeed essential role in both his PhD studies and subsequent development of his audio business interests. He's keen to ensure that others, especially engineering students, are aware of and can benefit from the exceptional opportunities offered by the AES in education, career development, and networking. And it's great pleasure of mine to introduce my friend and colleague, Mike Turner, to talk about transformers.
Thank you very much, Jamie, for the introduction, the kind words. Nice to see you too. I'm laughing because of something that's on the chat that I really can't repeat, but if you're here, you'll know why. We know, yes. Sorry about the feeble pun in the title tonight. That's what happens when there's a deadline and the AES newsletter has to go out and you can't think of anything else. The misunderstood transformer. It was a sort of an engineering brief that I did about 8-9 years ago now, goodness me, in Paris. And for those of you who remember the engineering briefs that the AES used to do, these were a kind of short paper describing an engineering topic in some shape or form. And it was only about 10 or 15 minutes long. That paper still exists. It's out on the e-library. And if you're not a member of the AES, then I strongly advocate joining. It's a great organisation. We have lots to offer, not least free access these days to the literally tens, probably hundreds of thousands of papers that are in the library, of which this is just one. So if you want a sort of paper synopsis of the kernel of this kind of talk tonight, then you can find it in that paper. The talk was far too short. This one is probably too long. I'll try and rattle through it. I've spent what seems like a lifetime drawing figures. So on with it without any further ado. The transformer. It's been around since the genesis really of electrical and electronic engineering as a science. Dates back to the mid-19th century, and like a lot of inventions that are important, it kind of popped up in a number of different parts of the world at the same time. You can see on the top right there an early transformer from Eastern Europe. I think that's Belgrade, and one at lower right, which is Westinghouse, devised by William Stanley, all from around the same time. Rather ironically, there's a lot of information about this on the Edison Tech Center organization. And I say ironically, of course, because Edison was a very strong advocate of direct current, and there were stories of the current wars at the turn of the century where Edison and Westinghouse were dreadful rivals. But that's obviously gone by, and the Tech Center now tells you all about transformers. But yes, instantly recognizable. It hasn't really changed very much. That's the point. Those are instantly recognizable as a toroidal and a laminated core transformer. And it's a bit like a student once said to me, gosh, this transformer thing looks very old fashioned. That's a bit naff, isn't it? And the answer to that was, well, no, actually, it's good because it tells you it's not changed very much for so long. It must have been about right in the first place. Point of view. Audio equipment and transformers, they are, as Jamie said, still an essential component, rather passé these days of DSP and filters and artificial intelligence and all the rest of it, but nevertheless a very important component, and that's really why I wanted to do a little bit of education on it and hopefully keep the knowledge of the transformer in the engineering domain where it's needed. We use them, of course, for power supplies, both 50 hertz, 60 hertz, just taking in the raw AC power, transforming it down to a lower voltage usually, and isolating us from the power utility from the mains. Or we use switch mode power supplies frequently as well for smaller transformers, which we'll hopefully see why shortly. Another very historically important role was impedance matching on transducers, the ins and outs of audio, as somebody once called it. In valve amplifiers, power transfer to the loudspeaker couldn't readily be accomplished without one because the impedance match was so awful. And they're also still used extensively in input stages of things like microphone amplifiers, moving coil phono, record player, gramophone cartridges, where the transducer is difficult to match with solid state amplification even to this day. Balanced and unbalanced interfaces too. There's very good reasons why a transformer still offers, some would say, the best rejection of noise. And then there's the safety aspect, breaking ground loops without disconnecting the ground or the earth wire from the mains plug, which of course none of us would ever do, would we? Electrical safety generally. So an important component, but one that you hear a lot of rubbish talked about, quite honestly. One of the trigger points for my original presentation was I read in a well-known hi-fi magazine a statement that this amplifier has a really big transformer because it prevents it saturating at high output power. Rubbish. Transformers do not saturate on load current. There's lots more besides that. You can read the slide for yourself. Some of these are off the internet. Some of them are from a book by a well-known studio engineer. And as a student, I found myself particularly confused by this sort of thing. Anybody else get confused by this? You take a transformer out, it's got windings on it, and it says 600 ohms center tap. Well, what about that transformer is 600 ohms exactly? The answer, just to confuse students, is of course virtually nothing, probably absolutely nothing, and we'll unpack why that is, what the reason for that labeling and how that's arrived at a little bit later on, hopefully. So our objectives of scope today, I'm not going to teach you how to design a transformer, so if you're joining for that, I'm sorry, I hope you won't be disappointed, it'll still be interesting, but the reason for not wanting to do that is, well, several-fold. Firstly, the transformer is a complicated beast. For all its apparent simplicity, there's lots of underlying compromises, and you need to make different compromises according to the application and the type of transformer and the circuit it's going in and so on. And really their design is pretty much a job for somebody who does nothing but designing transformers. It's a bit like doing, I don't know, fluid dynamics or something like that. You may understand how it works in principle, but actually you need somebody who does it every day to push the buttons and deliver a good result. So we're going to talk about the underlying physics. We'll build up an electrical model of the thing. We'll have a look at why they behave as they do. And the phrase, the answer lies in the flux, comes from an old university professor lecturer of mine called Michael Stevenson, who used to advocate this over and over again. Think about the voltage, the answer lies in the flux. And it's thanks to him you'll hear that today. We'll think about the key parameters and what you need to think about when you're designing with transformers and when you're specifying them so that you can make better use of them, and how their non-idealities, if you can use a phrase, are an influence on the audio performance, so they limit the performance. We'll have a look at a bit around some audio applications as well, principally, maybe a couple of power supplies. And we'll arrive hopefully at a qualitative at least understanding of all the design compromises that are involved, and hopefully at the end of that you'll understand, one, I haven't got time to teach you to be a transformer designer, and two, it's a job best left to the specialists in many cases anyway. So what do the textbooks say about a transformer? Pick up your school physics book and it says something like this, I think. These relations are actually approximate for a number of reasons. Firstly, they don't take account of the winding resistance. They also, as I shall unpack in detail, neglect the magnetizing current that's needed to support the flux, and that's a really important concept that we'll come into shortly. They assume that the windings are perfectly coupled, and there's lots of other things like stray capacitance, core losses, hysteresis loss, that kind of thing, that probably don't need to feature in the model, but you need to be aware of. I'm going to skip over this, I think, fairly quickly. There's lots of questions. How do we determine the flux? When will the transformer saturate? That sort of thing. We've talked about how the impedance marking on a transformer relates to its actual properties, and we'll show a bit of an apparent paradox later on that we can prove with those earlier relations, N1I1 equals N2I2. We can prove there's no flux in the transformer at all. So how does it work? And what do we do with power supplies? We'll come into those in a lot more detail later. I'm going to start by talking about an ideal transformer. Why is that? Well, the answer is simplification. Simplify, simplify, simplify. Strip the thing down to its very bare basics, and then we'll put it back together again bit by bit, and hopefully that will be insightful. Hopefully you'll agree it is. The ideal transformer, it's got a core, magnetic core. It's got two windings, just like the picture you saw at the start. It could, of course, have more windings, but let's start with two. The core is infinitely magnetically permeable, and we'll unpack what that means in a minute. That means the magnetism can flow around the core without any losses or any need for any current to support the magnetic field. And there's no limit to how much magnetic field, how much magnetic flux, as it's called, the core can carry. We've got no resistance in the windings, and the two windings are perfectly coupled. And that's going to be conceptually useful, even as it's unrealistic. Probably the most important thing you need to know about a transformer, apart from the basics of Ohm's law, is Faraday's law. Faraday's law of electromagnetic induction, and I'm sure it's written in very quaint English at the time, but it basically says that in a winding, the voltage in that winding is equal to the rate of change of flux linkage. And by linkage, we simply mean how many turns of wire does the magnetic field go around. So we end up with, if you put it in maths, it's V, the voltage, is N turns of the winding multiplied by the rate of change of magnetic field. Don't worry about the calculus if you don't do math. V equals N divided by dt simply means the voltage is proportional to the rate of change of magnetic field, and of course to the number of turns. More turns, we get more volts. More field, we get more volts. If we move the field faster, we get more volts. Very important to the transformer. We can turn the whole relationship round as well. In this illustration, we're moving a magnet inside a coil to generate a field. To generate some voltage and then some current. In this, we're doing the opposite. We're putting some voltage on the winding from, in this case, a battery and a switch, and we're creating a field around. So the thing works reciprocally, if you like. Voltage can create a magnetic field, a rate of change of magnetic field strictly. Be careful about that. Applying a voltage to this winding causes the magnetic flux to rise steadily at a rate that's determined by the applied voltage. Okay, and the magnetic field, by the way, is measured in Webers, so the flux rises here at so many Webers per second, and that's determined by the ratio of the voltage and the number of turns. It used to be measured in Maxwell's, and if we were to ask ourselves how much field there is in a given space, that leads us on to the concept of magnetic flux density. How much magnetism is there in a certain space, and that's measured in Tesla, in the days when that meant a Serbian engineer, nothing to do with present zeitgeist. We could change the name back to Gauss or Oersteds, I suppose, but that would probably be an offence to Tesla. But measured in Tesla and measured in Webers. And if I keep clicking, hopefully the slide will move on. Yeah, hopefully you're all familiar with Ohm's law, which is the relationship between voltage, current and resistance. Hopefully don't need to say much about that. It simply says that the current flowing in a circuit is equal to the applied voltage across a conductor. And there's this thing called Hopkinson's law or Rowland's law. Mr. Rowland was an American physicist, as was Mr. Hopkinson, and I think there's some confusion arose because Hopkinson made this law well known, but actually it was attributed to Henry Rowland in the first instance. It is, don't know why that one popped up there, it is basically Ohm's law for magnetic circuits, and it says that in order to drive a certain amount of magnetic flux around a circuit, we need a given number of amp turns, so we need some current and we need a number of turns in a winding, and the amount of flux that we get for that given magnetomotive force, as it's called, that was a term originated by Rowland, by the way, the amount of MMF that's needed to drive a certain amount of current is proportional to this thing called reluctance. So it's exactly the same as resistance in a magnetic circuit. We also in the magnetic world have a thing called permeance, which is the corresponding equivalent of conductance. So if we have high permeance, it's easy to drive magnetic field around a circuit. We don't need much current. If we have high reluctance, it's difficult. So iron, for example, has low reluctance and high permeance, and air has the opposite. Okay. Animation's gone a bit crazy there. It's a good reason not to use it. Yeah, reluctance, reciprocal of permeance. Just wanted to show you this little diagram, really. This is an example of what we mean by reluctance. It's a very, very simple magnetic circuit. The yellow bit is an iron core or steel core, which of course has low reluctance, high permeability in the vernacular. And it's got an air gap in it, which has high reluctance and low permeability. And the total difficulty, the total reluctance around that circuit is the combination of the reluctance of the iron and the reluctance of the gap. So you add them together just the same way as you would in a resistive circuit. And if we put n turns of wire around the wire and put some amps through it, we have Ni times the Ni in terms of magnetomotive force, and the total magnetic flux is then simply equal to that divided by the reluctance. Good. So in short summary, all the maths you're going to need is basically this. We need to know about Ohm's law, which says that the voltage drop is proportional to current and resistance. We need to keep in mind Faraday's law that says that the voltage on a winding, a magnetic winding, is equal to the rate of change of magnetic flux. We need to think about Rowland, Mr. Rowland's law that says the amount of flux we get for a given current is equal to the current divided by the reluctance, the ampere turns divided by the reluctance. Or we can turn that round and say how much current do we need? It's how much flux we've got divided by the reluctance of the magnetic circuit. And if we go back to the geometry, just skipping back to that, this core's got a length and it's got an area, and the gap's got a length and an area, and we can calculate from those this L for length, A for area, and mu being the overall permeability of the circuit, we can calculate the reluctance of the circuit, and therefore we can calculate how much field we get for a given amount of current. Finally, to translate this into terms that electrical and electronic engineers are more familiar with, perhaps, we have this concept of inductance, which is simply another way of saying how much flux do we get for a given current. And it's simply defined as flux linkage divided by current. Flux linkage per unit current is the definition of inductance. And that's a good term to remember. If ever you're wondering what is the inductance of something, think about flux linkage for a given amount of current. Flux linkage per unit current. And if all these formulae are a little bit unfamiliar, you can plug into Henry's law the expression for magnetic flux. Flux isn't something that we kind of measure on an oscilloscope or see in front of us on the workbench, perhaps in the electronics lab. And if we plug into the formula for inductance, the N turns times the flux, we plug in for the flux, we end up with this relationship N squared mu A over L, and that's perhaps a bit more familiar, N squared being the number of turns, so the inductance goes up in a given component with the square of the turns count. The permeability of the circuit also increases the inductance. So if we make it with iron, we get lots of inductance. If we make it with air or ferrite, we get less. A and L are simply the area and the length of the magnetic circuit, effective values if you've got more than one material in there. So back to that ideal transformer. Remember the assumptions that we said. The core was infinitely permeable. We've got no limit on how much flux it can carry. The windings don't have any resistance, and they're perfectly coupled to one another. And then let's carry out a thought experiment. I think these are valuable things, thought experiments. Let's apply DC, direct current, or direct voltage, I suppose, really, a steady voltage to the transformer. So an ideal battery and a switch. Let's close the switch and we get a voltage on the primary of the transformer like that. What happens next? Well, we remember Faraday's law. Flux rises at a rate determined by the voltage, so dphi by dt is constant. We have constant voltage on the winding, we have a steady rate of rise of magnetic field, and the flux will carry on rising on and on and on indefinitely, because there's nothing to limit it, there's no resistance in the circuit, there's no limit on the amount of flux density that the core can carry. And because the flux is rising continuously, we can apply Faraday again. What's the voltage on the secondary? Well, it's the rate of change of flux linkage, which is the turns on the secondary multiplied by the rate of change of core flux. So we get another steady voltage on the secondary, just scaled up by the number of turns. And there's no current flowing anywhere, because remember, Mr. Rowland said the amount of current we need to support this field is proportional to the reluctance of the core. And the core doesn't have any reluctance. It's ideally magnetically permeable, infinitely permeable. So if we put DC on the input of the ideal transformer, we get DC output. We can leave it there forever. Gosh, a little bit counterintuitive and certainly not real world, but that is the truth. If we had zero resistance in the windings and an ideal core, that's exactly what we would get. And if we had only had some superconducting wire, we could make one. But let's come slightly back down to earth and reintroduce some finite permeability to the core, reintroduce some reluctance. If we remember what happens last time, we closed the switch, we put some voltage on the coil, on the primary winding, and we got a steady increase in magnetic field. Nothing's changed here. We've got the same voltage on the primary winding. We haven't put any resistance in there. And therefore the magnetic field climbs steadily without limit again at a rate determined by the voltage and the turns. We've got finite permeability in the core, and that means that if we remember Mr. Hopkinson's rule, that we're going to need some current to support that field. The current is proportional to the flux and divided by the area of the core and the number of turns. So we get this concept of there being some magnetic flux in the core and there being some current needed to support it. So we've got finite flux and finite current. And if we remember what Mr. Henry said is that inductance we define as flux divided by current. That means we've got a conceptual magnetizing inductance in here. But don't worry too much about that. The point is, the key point to take away from this is that there is always going to be, in reality, some current needed to support the magnetic field. The voltage applied to the winding and the time determine the amount of flux we've got, and the permeability of the core determines how much current is needed to support that flux. Magnetic materials, they aren't infinitely permeable, and they're not able to support necessarily infinite amounts of field. A vacuum or non-ferromagnetic materials generally can take as much field as you want to put in them. Iron most certainly cannot. Iron and ferrite and things like that have curves that look much more like this, and you'll see the electromag people describing their materials with curves like this. It's called a BH curve, B being the symbol for flux density, the amount of magnetism in a given area of core, and the H being the ampere turns that we're applying to drive the magnetic field around that core. That MMF sometimes called magnetic field strength, and I find that rather confusing because magnetic field strength to me means flux and flux density, but I'm going to just use the term MMF, magnetomotive force, or ampere turns, and you end up with curves that look like this. So as we start from zero, of course there's no current, no flux, we build it up, and to begin with we've got a linear relationship between current and flux, but as the flux density in the core gets greater and greater, it starts to saturate. The permeability, which is the gradient of this curve, drops, and we start to see the evidence of what's called magnetic saturation. And it's generally symmetrical, and you'll see there's a slight, in these experimental curves, there is actually a slight difference between the curve on the way up and the curve on the way down. There's actually two lines there, and that's called magnetic hysteresis, and we'll come back to that a bit later on. It's a source of loss and distortion. Okay, let's look back at the ideal transformer again. My animation's gone haywire, I'm just going to go straight through it. Let's have a look at what happens when we put magnetic saturation back into the transformer. Well, the volts remain the same as before. We close the switch, put a step of volts on the winding. The flux climbs, therefore, at the same rate as before. No reason why it wouldn't. Faraday's law holds true. But now we're seeing a drop in magnetic permeability at the higher levels of flux. The flux is reaching the points on that previous curve where the permeability is dropping. And the result of that, again from Mr. Hopkinson's law or Mr. Rowland's law, is that the amount of current needed to support the field starts to rise. So instead of getting a nice straight linear rise of current, we start to see the current tipping up. And that means that the magnetizing inductance is starting to drop. The interesting thing about this, keep in mind that if we're feeding the transformer from a voltage source, the output voltage is unchanged because the flux is unchanged. So core saturation doesn't necessarily cause any harm to the output voltage unless we've got some resistance in the circuit, in the primary circuit, and we'll put that back in now. And what happens then is that instead of all of the voltage being available to drive the flux up all of the time, as that magnetizing current builds here, we will get a gradually increasing voltage drop across the winding resistance. And that reduces the voltage V1 here that's available to drive the flux up. So as the flux builds, the rate of climb of flux starts to decay. That's the definition of a first order differential equation for those who like such things. And it results in these exponential waveforms, the current rising steadily. And eventually we get to a point where all of the voltage is dropped across the resistance and none across the winding. If there's none across the winding, the flux stays constant here. The current is defined by Ohm's law, V over R. And of course, the secondary voltage dwindles away to nothing. Why? Because the rate of change of field has dwindled to nothing. The field is still there, but it's constant. And that's much, much more familiar and much more intuitively comfortable for us all, isn't it? Okay. Those are the key points so far. Remember Faraday's law, rate of change of flux is proportional to voltage. Remember Mr. Rowland, who says that the amount of current that we need is basically a function of the permeability, the permeance of the magnetic circuit. And that Mr. Henry says that tells us how much inductance we've got, essentially, the current and the flux ratio. And that when we introduce winding resistance or winding impedance, voltage drops are going to reduce the available voltage that Mr. Faraday's law sees, if you like, to govern the rate of change of flux. Okay, deep breath. Bear with me, we are getting to the more interesting stuff. All transformers are, of course, ordinarily fed with alternating voltage, alternating current. So the waveforms look something like this. We apply a sine wave of voltage, we get a cosine wave of magnetic flux, we get a sine wave of voltage on the output. And perhaps the only sort of, not surprising, that the important thing to notice about that is that because the magnetic field is proportional to the voltage time product, that's to say the integral of voltage over time, we're driving the flux up over the entire half cycle of voltage there. So from the start, it builds and reaches a peak at the zero crossing of the voltage. And that's why you've got the sine wave here and a cosine wave here. But importantly as well, it also means that the magnetic field is proportional to the inverse of the applied frequency as well as the voltage. So as we drop down the frequency, so let's say we're driving the transformer from a signal generator, or a valve amplifier, or whatever you like really. But as we drive the transformer and we drop the frequency down, the core flux is going to increase in inverse proportion with the frequency. It'll double for every halving of frequency at a given voltage. And that means that the transformer core is being worked hardest at the lowest frequencies. I won't dwell on the phasor diagram. These are useful things. If you've done an engineering course, you'll recognize them and probably recoil slightly, but they are very useful for thinking about the transformer. I'm not going to remotely try and explain that online. It's the sort of thing you really need to just sit down with a pencil and work out for yourself to your own satisfaction. Let's look at a transformer now with some load on it. And what I'd particularly like you to look at is the winding currents here. We're going to put voltage on the primary as before. Let's not worry about the resistances for a moment. We're going to put some voltage on the primary. We'll generate a secondary voltage, and that will generate some current in the secondary winding. Everybody hopefully comfortable with that. What now happens is that we've got current in the primary, N1I1, and we've got N2I2 in the secondary. And by our conventional definitions of the current, they're in opposite directions. The current is flowing conventionally from left to right on the primary, and if we use conventional current, it'll be flowing from right to left on the secondary. So left to right on the secondary as well. So we will find that when we add the net ampere turns together, we get zero. The currents in the windings are, when we define them this way, equal and opposite. Well, that means there's no net ampere turns at all. If you remember, N1I1 is equal N2I2 from the physics books. That means there's no net ampere turns available to drive the core flux. What on earth is going on? Because that means there's no flux in the core and the transformer couldn't work, could it? So there's a bit of an apparent paradox there. The answer, of course, is that if you imagine if the flux, just say if the flux did drop like that, what would happen? Well, we'd lose all of the induced voltage in the primary winding, and all of the voltage from the supply would end up across the resistor, and we'd get a huge current flowing. And that would in turn try and establish some field again, because it would be greater than the secondary ampere turns. So actually what happens in practice is that as you load up the transformer, the amp turns on the primary increase because the voltage here drops ever so fractionally slightly, and the ampere turns keep themselves in balance but never completely cancel out. There's always a little bit of net ampere turn left, and that's the amount that's needed to support the flux in the transformer core. So what happens when you apply a load is that the voltage here drops very slightly because of the primary winding resistance. The voltage on the primary drops too, and that means that the flux in the core drops a little bit. So loading up a transformer, loading up a voltage-fed power transformer, actually decreases the magnetic flux in the core and gives the transformer an easier time from a magnetic perspective. Obviously it heats the windings up, and that's the reason why we can't carry on doing it indefinitely, but nevertheless the core is not the problem when it comes to loading up a transformer. And just to go back to phasor diagrams again, I drew them for the power transformer on load here, showing all the different currents that are flowing, the magnetizing current in the primary that supports the flux, the primary current itself, the secondary current, and the voltage drops and so on. And I think that's a good illustration of why I say, you know, the voltage determines the flux. Think about the voltage, because you've got 4 different currents on there. We've got the input current from the source, we've got the magnetizing current, the internal primary current, the secondary current of the transformer. Which of those determines the flux? If you want to work from current, well, the answer is a combination of them does, and you can work it out that way if you really want to, but you'll need to know the permeability of the core and how it saturates and so on. Whereas if you work from voltage, you just need to know either the primary or the secondary voltage, and possibly the drops across one of the impedances. So a much easier way of working, and that's why I would always say, if you can, work from voltage. There are instances where that's not possible, where the transformer is fed with current, and we'll come across a couple of those a bit later on. Okay, bear with me for one more thought experiment. We've built up a transformer model here now. We've shown some resistances and the magnetizing inductance. We've got one bit missing, and that's what happens if the windings aren't perfectly coupled. What does that mean to us? Let's, to explore that with a thought experiment, short circuit the secondary winding of the transformer. Just checking the time. You can see that we have defined the secondary voltage as 0, therefore there can't be any flux in the core. This is an ideal transformer again, no resistances. What happens then? We've got no flux in the core because the secondary is shorted. The primary voltage must also be 0 therefore, and we end up with this enormous current flowing. Now, we mentioned before about the reluctance of the magnetic circuits, and if all of the flux was flowing in the core, then there would be an infinite current flow in this scenario, or at least limited only by that external source resistance. But if the magnetic coupling is imperfect, what happens then? Well, some of the magnetic field is going to make its way through the more difficult path of not going around the core, and most of it will go around the core, but a little bit of it will leak around the local windings. And with that enormous current flowing in the primary winding, with no flux in the main core, we will establish a leakage field around the primary winding that doesn't link the secondary. So again, we've got a big current now in this short-circuited transformer, no flux in the core, but a little bit of flux locally around the primary. And the flux divided by the current is called the leakage. And if we think about that experiment the other way around, if we flip the windings over, we could see it's exactly symmetrical. So we'll have leakage inductance on both sides of the transformer. We can work that out from current. I'm not going to dwell on that for reasons of time tonight, but you can think about it if you split the primary winding into a bit that links the flux and the rest of it that doesn't. and you can work it out from voltage if you wish. But that gives us this more comprehensive circuit model that looks something like this. It's got resistances on each side of the windings, the ohmic resistance of the copper wire or the silver wire if you're really posh. It's got some leakage inductance on each side. It's got a magnetizing inductance that we'll normally put on one side or the other, not both, because we're usually driving both windings, but the transformer in the middle is ideal, so we can put it either side anyway if we choose. Winding capacitances. We've talked a lot about resistance and inductance. What about capacitance? We've got a lot of bits of wire in close proximity to one another and in close proximity to a core. So that means we've got some capacitance in several different places here. We've got capacitance from turn to turn to turn to turn distributed throughout the winding. Likewise on the secondary. We've got capacitance between the windings and some to the core. These are distributed, of course, and therefore, how do we model those? Well, the answer is, for practical purposes, we're going to use what's called a lumped parameter model. We'll lump all the capacitance and pretend it all appears across the primary and the secondary windings and a single capacitance from the windings to ground. So it looks something, the total model looks something like this. We end up with some shunt capacitance across the windings, and that resonates unfortunately with these leakage inductances to give us a low pass type response. How do we minimize that? Well, we use fewer turns on the windings. We can keep the windings apart from one another, keep the turns apart from one another, spacing the windings out. That worsens the leakage inductance, so there's the first compromise. And we can also damp it, as we'll show a bit later on, with loading at the output of the transformer. The capacitance between the windings bridges the transformer action and carries high frequency currents directly from the primary to the secondary, so that degrades noise immunity in things like microphone amplifiers. If the transformer is in a switch mode power supply with some fast switching voltages on one side, it's a serious interference noise source on the other. So if you're supplying your low noise audio equipment from a switching supply, you need to think about that. We can space the bobbins out. That increases the leakage inductance again. You'll spot a pattern here. There's lots of compromises popping up. And we can most effectively put an electrostatic shield in between the windings. That's usually a turn of foil that's not shorted together at the ends. It overlaps, but it doesn't short circuit, and it provides a barrier, electrostatic barrier. Capacitance to core, that's similarly an EMC path, electromagnetic compatibility issue, puts current into the ground. And it's again important in switching supplies and mic preamps and things like that. And distance and electromagnetic shielding, electrostatic shielding are your friends there. And that takes us to this sort of list of villains. We've talked about winding resistance. What does that do in an audio context? Well, it puts resistance loss into the circuit, so we get a dB or perhaps more of insertion loss. We get noise from it. Efficiency is a penalty in power transformers. And we fix that by using thicker wire, basically, or if you really want to go there, silver wire, but it's not much better and it's a heck of a sight more expensive. Magnetizing inductance, that's a shunt element that goes across the windings. So that tends to carry current at low frequencies away from the circuit that we want. So it cuts bass in an audio context, reduces the low frequency end of things. And we saw that that's got saturation characteristics. It's also got that hysteresis that we spoke about. And that's a source of distortion potentially. And we can avoid that by using the right kind of core material. If we want to keep the inductance large, we avoid air gaps. We can put more turns on, but of course that increases the capacitance and the leakage inductance. So again, all these compromises start to pop up. And leakage inductance, that's in series. So that's reducing the transmission of the current at high frequencies. It resonates with the winding capacitances, so we get a low pass response. It's the thing that limits the transformer at high frequencies above all else. In power supplies, it can be a problem because you get overshoots of voltage and nasty things happening there. And you can minimise this by putting a strap around the transformer, and I'll show you a picture of that later on, the belly band as it's sometimes called. And the final sort of bit of non-ideality I just wanted to touch on is core losses. We saw the magnetisation curves of the core earlier, looking something like this, and that's an indication that when you push the field up and then bring it back down again, you don't get all the magnetic energy back. You're doing work in realigning the magnetic domains, and that causes some loss. It's a change in the permeability of the core, because remember the permeability is B to H ratio, so we can see on this curve that the slopes are changing instantaneously as we go from one side to the other of the loop, so we get distortion from that. Eddy current loss is probably more of an issue in audio transformers. We've got a core that conducts electricity as well as magnetism very well. We get circulating currents within that material because of the field in there, and that causes power losses. And we can show that as a shunt resistance across the winding here. So we put it all together. We end up with this rather complicated, or potentially complicated circuit model with the primary resistance, the secondary resistance, the leakage inductances, the magnetizing inductances, all those stray capacitances, and a bit of a hand wavy thing there called the magnetizing losses, which a resistor is not a bad model for in terms of eddy currents. It's pretty lousy for hysteresis, and the power people use a resistor there just because it's easier to represent the amount of loss at a given operating point. In reality, we don't need to think about all of these elements all of the time. You may heave a sigh of relief. We use the ones that make sense. If we're driving the transformer from a voltage source at low frequencies, we can probably ignore the stray capacitances, or at least we can ignore them at the low frequency end of things. We can take care that we shield the core, so we don't need to worry about the primary to secondary coupling. We'll make sure that we have little capacitance to the frame, so we can strip all those out. We can move what capacitance is left onto the secondary side and just assume it's there alone, because the primary side is driven by a voltage source, so the voltage source isn't going to care about the loading particularly. It'll need a bit more driving current at high frequencies, that's all. And we end up with a frequency response curve that looks something like this. This would be typical for an audio transformer. It's got a gentle roll off at the bottom end because of the magnetizing inductance and the primary resistance. And it's got a peak and a steeper second order roll off at the top end because of the inductance, which I've lumped into one space again from the primary and secondary. And it resonates with the winding capacitance to give us this quite pronounced peak, actually, sometimes if you don't do anything about it. Okay, deep breath. Transformers at large, as I've called it. Just not a comprehensive list, because I've already taken up a lot of time. Just to look at a few interesting examples. Of course, the archetypal mains power supply, 50 or 60 hertz on the input side, low voltage to your power amplifier or whatever it is that you're driving, and through a rectifier. We have a screen to keep out noise from the main side, stop it getting into the audio. And as I've said before, you don't need to consider the transformer power rating at the peak loading of the amplifier, the peak output of the amplifier. We can do it thermally on the basis of average load for the amplifier. The only thing you do have to watch is that the winding resistances are small enough. And if you're designing a power transformer for an amplifier, that's probably going to be the thing that dictates the size of the transformer. You need enough core space to put a big enough winding in there to keep the resistance down. And another gotcha in these is that because we're charging capacitors up every cycle with little pulses of current, the rectifier diodes only conduct at the peak of the incoming AC. So we get waveforms on the secondary and on the primary that look like this. And those are very far from sine waves. They've got a much higher root mean square ohmic heating value relative to the amount of power that they deliver. The power factor, if you like, of those windings is about 0.5 or 0.6 typically. And it means that if you want 100 watts out of the DC side of the power supply, you're probably going to have to size the transformer for something like 200 VA in order to do that continuously. And that's because of this rather nasty peaky waveform. Another gotcha in low frequency power supplies is the switch on. If you switch on at the zero crossing of the mains, then what happens is you've got the whole half cycle at the start to build up the field, and the flux density builds to twice the normal working value, because it doesn't start from in the steady state, it starts from a negative value, but at switch on it doesn't, and we end up with this transient of flux, this standing DC component of magnetic flux in the transformer that gradually decays away with the winding resistance driving that down. If you switch on a mains transformer, you'll have heard it yourself. You go dong, and the whole case of the amplifier shakes a bit as you go through this transient. And that's an example of a real one. I measured that in the lab myself. It's a toroid 700 VA, so its continuous current rating would be 2 or 3 amps on the primary. But it's got an 80 amp switch on peak. Ouch. Unfortunately, although we can fix that by switching on halfway through a half cycle, switch on at the peak of the voltage, and you can see there that fixes this beautifully. The problem with that is that then the voltage on those capacitors here jumps up from nothing to the maximum value instantly, or almost instantly, limited by the impedances. So you get a blooming great thump of charging current on the capacitors. And really the only answer to that is to use some sort of current limiting arrangement. If you can't live with it and just accept the overload current for a short time, and most equipment frankly does, then you need something like that. And there's some nice pages by a guy called Rod Elliott in Australia you may be familiar with. He's got some very nice illustrations of that, so I won't dwell any further. But there are things like thermistors you can use. Not much cop in a Class B amplifier because there's no current most of the time, and a better solution is a series resistor and a relay or something like that. This was a nice little illustration just to come back to Mr. Rowland and his saturation and the loss of permeability. This is what happens in a power transformer or any transformer when you overload it. You've got the core saturating, the flux going up and down, and the current that results from that. The one thing I wanted to just talk about here was first of all, you'll notice there are harmonics in the current there, quite bad harmonics, in addition to those that we talked about from the rectifier. And also, why do we want to avoid saturation? Well, this is one reason, because it causes loss and noise and other things. The actual truth of the matter is that we could continue to make the core smaller and smaller and smaller if we weren't bothered about the current waveform. And again, the sizing of the core in practice, remember that the current doesn't cause saturation. We could continue to make the core smaller and smaller and smaller, provided that we can cope with this magnetizing current. And some transformer manufacturers, will offer low saturation ones for various reasons that obviously cost more because they've got a bigger core in them. But the core isn't there to support the current; it's there to support the flux. And we put a big core in to avoid having too much magnetizing current, and to allow there enough space for the winding to fit without having a lot of winding resistance. Noise in transformers, yuck. Buzzes and zingings and hums and things. Those come from really 3 sources. You've got current in the windings, you've got a magnetic field around them. Current crossed with flux gives you force, so the windings are constantly trying to move. The core itself will expand and contract slightly, magnetostriction as it's called. That happens based on the amplitude of the field, not on the polarity of it. So it's kind of a full wave rectification effect that you get a swelling and a shrinking of the core twice per cycle. So we get 100 hertz or 120 hertz buzz in the harmonics from that. And both of those get worse when we've got more flux in the core. So that's a reason to keep the core flux down. The harmonics in the current in the secondary itself, like diode current, also interact with the magnetic field and cause buzz. So the thing gets noisier when you put it on load. And the problem with the harmonics is that they're much more audible. Of course, your ear's very sensitive to higher mid-band frequencies, and generally speaking, the acoustic resistance into which they're radiating is increasing, and you get much more efficient coupling to the air of those higher frequency harmonics. One last point about transformers used for power supplies. In the old days, and some of you may remember this, a lot of you probably won't, TVs and radios had half-wave rectifiers in them because they were cheap, and they also, once upon a long ago, allowed connection of the equipment to a DC power supply as well as an AC one. And that used to cause direct current components on the mains supply, and therefore a standing voltage. If you put your fluke meter across the socket, you might see a fraction of a volt of DC as well as the 250 volts of AC. And that low voltage DC will push current through the transformer primary. It shifts up the operating point, as you can see in the graph here, and that means we bang our heads against saturation in one direction earlier than we otherwise should, and that again causes noise. And you can get around this by, I've never seen this done in a commercial amplifier, although somebody will no doubt tell me it is. Rod Elliott again's got some nice discussion about all of this, but you can basically put capacitors in series with the transformer primary to couple out remove the DC from the transformer. The rectifier diodes are across there just to prevent any large voltage developing across the capacitors if something goes horribly wrong. But that's a good way of avoiding those strange noises you may hear from transformers. There was one brand of amplifier was notorious for humming away at different times of the day and night. Their brand will remain nameless. Leakage flux, we talked a little bit about that earlier on, and I just wanted to touch on this as well because it has influence in things like noise again. Transformers radiate fields from little gaps in the core particularly, and around the windings, and that can introduce hum into other things. And in the old days of valve amplifiers, people used to arrange the transformers perpendicular to one another to try and minimize cross coupling. And it's good practice in transformers generally to interleave the laminations, like I hope you can just see in that figure there, to avoid gaps in the joints. And the ultimate expression of that, I guess, is the toroid, where you just wind the thing from a continuous strip so there's no gaps at all. Also, if you operate at high flux density, the permeability, remember, of the core drops, and so there's more encouragement, if you like, for more incentive for the field to spill out because the iron isn't conducting the field as well, if you like. And the final thing you can do is to put a strap around there. People call that a belly band sometimes. Copper foil, usually wide, to give low resistance. And the idea is that if there is any flux that leaks out of the core, it cuts this shorted turn, and that turn carries a lot of current and opposes the stray field from the transformer. You'll see that quite a lot on switcher mode transformers, not so often on 50 Hertz ones, but the Japanese used to do it quite a lot. Okay, hum fields also, of course, get into other transformers and cause hum. Again, distance is your friend, but so also can soft iron shielding cans, screening cans, and you'll see those on these typical microphone transformers. Audio apps, impedance transformation. If you look at the ratios of voltage and current on the primary and secondary, they go with the turns ratio, and because the volts go up and the current goes down, or vice versa, the impedance goes with the square of the turns. Very useful property. It allows us to match a high impedance to a low, or a low impedance to a high one. And that was very, very important, as we'll see in a minute, in valve amplifier days when speakers were a few ohms still and the amplifier needed a load of a few thousand ohms. It's also important for reducing noise in input stages. Amplifiers using particularly bipolar transistors, have both noise current and noise voltage in their input stages. We can draw an equivalent circuit like this. That current flows in the impedance of the source, reflected through the transformer, and is added to by the voltage noise. So if we have a big turns ratio on the transformer, this impedance is big, and we get a lot of noise from the current. The IN times the impedance gives us a lot of noise voltage. So the noise contribution from the current becomes very large indeed because of the high impedance. If we have very few turns or no transformer at all, then the noise voltage dominates, and there's a happy medium somewhere in the middle, which is the impedance match. And transformers are very important for that, even to this day, for things like ribbon microphones and moving coil phono cartridges. It is possible, of course, to do it with solid state electronics, but it's still quite difficult to get the noise as low as you can with a transformer. Impossible, I would say, in fact. Balanced inputs, very, very useful for this. There's a gentleman called Bill Whitlock who's done some lovely papers on this, and quite rightly says the transformer is probably the highest expression of rejecting common mode rubbish noise voltage that's common to both inputs on, say, a microphone cable. The voltage appears at both terminals at the same time, and is rejected by the transformer, provided we don't have any stray capacitance bridging primary to secondary. Can't do much to eliminate the capacitance entirely, but what we can do is put a screen in there, and that means that the noise current then flows hopefully harmlessly to earth. Don't make the mistake of tying the screen to the little 0-volt trace on your op-amp circuit, because all that happens is the noise current gets injected into the ground of your equipment, and the ground will then propagate it. You'll have impedance resistance in the ground, and then you start to see the noise all over the place. And once it's in there, it's almost impossible to do much about it. So it used to be called the pin 1 problem. Again, some nice papers on that in the AES, and a very good standard that I used to insist all my engineers in the motor drives business read. And you'll see that I talked about loading the transformer earlier. To avoid that nasty peak, we can put this thing called a Zobel network in there, which damps down the resonance between the primary and the secondary windings. We've got that. If I go back to the equivalent circuit, it's here somewhere. Where the heck is it? Go all the way back. There it is. If I go back to that equivalent circuit, we've got this resonance between the inductance and the capacitance, which can be damped just by a load resistance. We can pop a load on there and that will deal with it. But the problem with that is very often we need so much load on there that we start to see, bear with me, we start to see a voltage drop which is significant in decibel terms. So with this transformer, in order to get it to not peak, I had to put about 2k load on there, and that cost me about 2 dB. The nice thing about the Zobel network is because there's a capacitor in series with the load resistor, the load is really only applied to the fullest extent at high frequencies where we need the damping. And so you can reduce the loading on the circuit, reduce the insertion loss, while still keeping the response substantially flat. And there it is, the Zobel network. Another point just to watch on transformers, when you put them in a feedback circuit, there is phase lag here, quite a lot of it, 180 degrees when we go through that resonance. There's also some phase lead at the bottom because of the magnetizing inductance, and those can adversely impact the stability of feedback loops. And in the old days of valve amplifiers, well, even with the modern valve amplifiers, because they're still popular, this is an enemy of feedback stability. And here we are, here's a valve amplifier, speak of the devil. Single-ended one. The only reason I wanted to show this really is it's a good example of where you've got a standing current in the transformer, and the magnetic point, therefore the magnetic working point, is shifted up from where it ideally would be at the origin up to this little red dot. There isn't a dot at the origin, it should be there. What we do in practice very often is put a gap in the core, and that softens the BH curve a little bit because it increases the magnetic reluctance in the circuit, and it means that we get less shift in the magnetic operating points. The penalty for that, of course, is that the magnetizing inductance goes down and we lose some base. So that's why if you're buying a single-ended transformer, you'll generally need a bigger one, because they'll try and maximize the magnetizing inductance while still allowing it to support a substantial DC current from the output device. Push-pull gets rid of that. There's a typical old-fashioned push-pull output stage, still again very popular with certain people. Advantage here is no net ampere turns, because if the two valves conduct the same current, the currents in the winding, the standing currents, are in opposition to one another, and so the core sits happily at its magnetic neutral point. The symmetry, we can cancel out even order distortion, which is nice, makes much better use of the transformer. The one thing to watch particularly here is if you drive one output device hard into cutoff suddenly, so you're overdriving your guitar amplifier, for example, the leakage inductance, there's stored energy in the windings, and suddenly the valve cuts off, the voltage on the transformer ends jumps right up to enormous values, in theory unlimited, but in practice limited by the winding capacitance and the rate of change of current. And if ever you've come across, as I have, guitar amplifiers that friends bring you around to repair and discover that the transformer's dead, got a shorted turn in it, that's probably why. You can get round leakage inductance in things like push-pull stages by what's called bifilar winding. You take two turns in hand. You can make trifilar or quadrifilar windings if you want. You can wind the primary and secondary all in one go, like it's shown here. The disadvantage, of course, self-evidently, is that you get a ton of capacitance between the windings. So it does a great job of reducing the leakage, but it doesn't do a good job of mitigating capacitance. So it's not necessarily good in applications where you want isolation between the primary and secondary. But there's nothing, of course, to stop you winding the two halves of the primary like that and then putting a third winding somewhere else, the secondary. And that arrangement was used in a thing called the Macintosh output stage, which you can look up online or in the Langford Smith book. Nearly done. Just a few little wrinkles that I thought you might be interested to see. Here's a neat little trick. Remember we said that the volts determine the flux. If we load a line input transformer, let's say, into the virtual earth of an op-amp, this point is held at ground by the feedback in the amplifier stage. And that means that apart from the secondary resistance, which is hopefully low, the flux in the core is essentially zero. We get a little bit of flux because of that resistance, but it's pretty darn small. And that means that we can use a tiny little transformer and get full bass out of it, which is rather nice. The leakage inductance still matters because it's in series with the circuit and it will appear in the transfer function of the amplifier. As is electrostatic coupling between the transformer's primary and secondary. I tried this and found it was dreadful until I put a Faraday shield in there. It's not great from the point of view of noise because the input resistance of the amplifier, which relates to the feedback and gives you the gain essentially, neglecting the resistance, your gains RF over RI still. These are in series like they are in any inverting shunt feedback amplifier, and therefore they add noise to the source. So it's okay for line inputs, it's not great for, not usable really for microphone inputs. And a gentleman called Paul Zwicky at Revox, Studer Revox, came up with a rather groovy patent using feedback and two transformers to provide a nice high impedance input while still cancelling the flux. Interesting idea, you can look that one up. There's a similar idea you can use on the output side. If you were to drive the transformer core from a negative impedance, subject close to my heart with my speaker work, you can cancel out the primary resistance of the transformer, or almost anyway. You don't go all the way to full cancellation, but you can go most of the way there quite safely. And that means that the amplifier's output voltage internally is equal to the primary driving voltage of the transformer. And if the core starts to saturate, well, so what? Because there's almost no voltage drop across the net impedance, because the net impedance is nearly zero. So by doing that, we can almost eliminate distortion from the magnetizing inductance of the transformer. And Doug Self, whose splendid book on small signal audio design, I nicked that figure from. Apologies to Doug, but I hope he doesn't mind. The book's excellent, well worth a read. You can do this sort of thing by applying a bit of positive feedback, positive current feedback around a transformer. However, like a lot of things, it's older than you think. The first time I saw this was in the early 80s at the BBC, where Calrec used to use it in their broadcast consoles. I think, by the way, Audio Precision probably mark the pinnacle of this kind of technique with their use of these sorts of ideas in the Audio Precision analyzers, and Bruce Hofer has a patent on it. But Calrec were there first, possibly with something a little bit different. Don't want to get into that, but Calrec most certainly had that in 1984 with this arrangement. Very, very nice example of electronic design. Why did they use a separate op-amp to load the secondary of the transformer instead of doing it with just one stage? Well, two reasons. They wanted a monitoring point that wasn't distorted, and that's what this gives you. And secondly, rather nicely and elegantly, instead of returning that distorted magnetizing current to the ground of the system where it could get into other things, it returns it back to the power supply. So a nice bit of, elegant and well thought through design there. So that's me done. I'm well over time, sorry about that. But in conclusion, think about the field. The answer lies in the flux. Far, far easier generally to think about transformers that way. The voltage determines the flux, and then a current is needed to support that flux depending on the permeance of the circuit, the permeability. Saturation occurs based on flux and time, not on current generally. There's a lot of equivalent circuit models that can be useful to you, which if used carefully can be invaluable, but you do need to think about which parameters to include where to make good use of those. And if you are into electronics, use of electronics intelligently around the transformer is a good way of making the best use of them. So that's a bit of a marathon, longer than I intended, apologies for that, but very happy to take any questions if you're still awake.
Thank you very much, Mike. Nobody's popped. I forgot to mention you could put questions into the Q&A box. So those of you that are still listening, please feel free to drop some questions into the Q&A box. We do still have a little bit of time on the Zoom link before they switch us off. I have one comment. The Macintosh amplifier used one-to-one feedback to the cathode, but interesting, one of the early quad amplifiers, the quad 2, I think it was, valve amplifier, used a slightly reduced form of cathode feedback. So it's not an uncommon technique to do that in valve output amplifiers. I wonder, okay, got a little, so I wonder if we've got any questions.
One point I would mention on that while anybody's thinking of a question is we talked about valve amplifiers and the need for impedance matching. One of the reasons why triodes were favoured in valve amplifiers as opposed to pentodes, apart from their distortion characteristics, is that they feed the transformer with a lower source impedance. And if we think about what we've said before, that voltage determines the flux and the current appears in response to that, the triode is closer to a voltage source and is therefore better at managing the transformer's tendency to distort the voltage waveform. As the magnetization changes in the transformer, it loads the valves up and down. If you've got a pentode or a bipolar transistor or even a FET in common source mode, the impedance is high and the transformer current can do what the heck it likes to the voltage waveform, and you end up with a distorted voltage waveform. If, on the other hand, you drive it from a very low impedance, then the flux is defined by the voltage. The output voltage is undistorted, relatively speaking, despite the nasty things that the magnetizing current might do. So not only are you getting lower distortion you're also controlling the resonances that I spoke of as well. You've got a nice low impedance, it damps those resonances. Was
Oh,
that a
right.
question?
Maybe I can have there's no questions yet in the quick Q&A thing, but your recent statement. So we really should not be driving transformers with a current source. Would that be correct?
I think that's true, provided that you remember the exception I showed a little bit earlier on. If you drive it into a zero impedance current sink, because then you're defining the flux as zero and the magnetizing current is negligible. I did show that a little bit
Yes,
earlier
you
on
did. So
there.
if we had a so should we ever get room temperature superconductors? If we had a superconducting voice coil, then it might be appropriate to drive our transformer coupled amplifier by a current source. Interesting.
Well, careful with that one, because if we had a superconducting voice coil, we'd still have the emotional EMF.
Oh,
So
yes, yes,
but
yes.
you're right, it would certainly improve matters. If we could wind the transformers with superconducting wire, then all sorts of things would be possible, because we could have vanishingly small transformers. You wouldn't need a big heavy mains transformer. You could have quite a lot of magnetizing current without any loss in the transformer. Whether of course the electric supply people would like that is another matter.
I think they would have your guts for garters.
And by the way, thank you. I meant to mention an acknowledgement from Menno in the questions. Menno van der Veen in the Netherlands, in Holland. Thank you, Menno. Menno's done a lot of work on valve amplifier transformers, and if you're interested in that sort of thing, I would say he is the person to talk to about novel use of output transformers in less conventional topologies than the ones I've shown. Some very interesting stuff done there. And I think I did put in the, no, it's not there. Sorry, I did have a slide. It's in the handout copy of some stuff to read. There are various recommended readings. Bill Whitlock's transformer stuff I've mentioned, and Doug Self's book I've mentioned. The well-known transformer manufacturers for audio like Sauter and Lundahl also have some very nice application notes on their website. So
Hmm.
have a look at those and see what you think. But I hope I've illustrated that different transformers and different applications have lots of different aspects to them, and that's really why, although it's important to understand those when you apply a transformer and know that it's got stray capacitance and know that the windings have self-inductance, leakage inductance, the minimizing of those things and the best compromise. And I think you were talking about this earlier, Jamie. You were mentioning interleaving of the windings and splitting them into sections and things. That's all
Yes.
about trying to minimize the capacitance and minimize the leakage inductance of the transformer. And audio output transformers were, you mentioned quad earlier, were designed with loads of layers of interleaving of the primaries and secondaries in order to try and stop the kinds of, or not stop, but to mitigate the misbehaviors that we've seen.
Yes.
Yeah. So the design of transformers, I would always say, leave to the professionals unless it's something pretty straightforward. You know, the people, the Lundahls and the Souters of this world, and the Jensens. And I'm sorry if I mention. There's probably a whole load of other people saying, "What about us?" And there are lots of other manufacturers you can find. They earn their money.
Right. Eric Winokur, not a question, just saying that he posted an article in Sound and Video Contractor about transformers, and he did drop the link to it in the chat if anyone's interested, just before it disappears forever. Um, uh, oh, Roger saying that, sorry, Peter Baxendale developed a circuit for the KEF KM1 and they apparently Minim used to assemble the electronics for that. Small world. While we talk about the triode versus pentode thing, and one of the issues, of course, and one of the reasons people went to pentodes or beam tetrodes was you got a bit more power out of them. You took a distortion hit, but um, they were able to run more power out of the system for a given supply voltage and valve dissipation. And of course, there was the famous or infamous, depending on your point of view, ultralinear circuit, which then put feedback to the screen grid to try and get, for want of a better term, the best of both worlds. People got quite creative with their transformers. Um, Still no questions. The one thing I would say, if you look at old circuits, especially old telecom circuits and filters, um, although transformers are difficult to design, as are inductors, in manufacture, once you'd sorted those things out, they were amazingly consistent in terms of their output. So you could actually do some quite interesting things. So just something to bear in mind when you look at these old circuits, think, why did they use all these inductors? Um, One was active circuits were very, very expensive. But the other one was actually inductors and inductive components could be made remarkably consistently once you'd sorted out the tricky bits. Um, okay, I
Oh, there's
think
a
we'll.
question from Alan Belcher. Um,
Ah, go
and
for it.
Alan's asking, is magnetic screening still used with transformers? The answer is yes, most definitely it is. If you buy line or certainly microphone transformers and gramophone, if I can use the BBC term, pickup transformers, will always be shielded, because otherwise you just get hideous amounts of 50 hertz, 60 hertz hum induction. The cans are usually made from soft iron, or I think it used to be called mu metal. I think mu being the symbol for permeability.
Yes.
Soft
Yeah.
iron, and it was vulnerable to being damaged by work hardening. But yes,
Mm.
magnetic screening very much still necessary. Doug Self says in his one of his books very appositely, however, distance is more effective than mu metal, and I think he's right. Distance and
Yes.
orientation are probably a better way to go, rather than trying to manage with screening, which in my experience ain't that effective. It's a lot better than nothing,
Mm.
but not infinitely effective.
I suppose I've got that brings up we talked about you showed a hysteresis curve and you talked about soft iron magnetic materials. Of course, things like ferrites are often quite hard. Um, do you want to say a couple of words about that in the
Sure,
minutes we've
yeah.
got left? The pros and cons?
I don't know. I'm probably displaying a picture of a beach or something at the moment, aren't I?
Yes, it's a very nice picture of a beach.
South Devon coast for those who would be interested in visiting. Sorry, let me find the screen share button again. Yep, and then I need to go back to that, don't I? Yeah, there we go. BH curve. Yes, the distance between the go and the return, as you say, and it's all about magnetic domains in the material. If you go, I'm not a materials physicist, so forgive me. I'm just telling it as I read it. But the magnetic materials are comprised of what you can think of as tiny little domains, crystals or whatever, which contain the magnetic dipoles. And as you magnetize the material with ampere turns, all of those little magnets line up inside. It's probably a horrible analogy, and the physicists probably hate it, but it's a good enough one for us ordinary folk. The domains all line up like little compass needles, and that's what gives you the low permeance effect. But when you then remove the magnetic field, those domains tend to stay a little bit aligned. If they stay aligned a lot, it's called a permanent magnet. So, neodymium, samarium, cobalt, all of the steel, in fact, is magnetically relatively hard. Whereas materials like soft iron, the domains let go quite easily when you remove the current that drives them. But if they stay in alignment, then you get curves that have a greater separation. And I think somewhere there is a, I know I had one with, let me scroll through. Remind me never to use animations again in PowerPoints. It's easier not to bother. Yeah, you end up with a curve on harder materials, as you say, Jamie, that looks like this. And as you're reversing all those domains, you end up traversing a different trajectory, which looks like this one. And then when you get back to the negative end of things, you reverse again. And yeah, aside of permanent magnet materials, which have very, very broad curves and huge amounts of what's called remnants, I think it's called retentivity on that particular figure, but remanence is usually the term that I would use. Aside of permanent magnets, you have quite a lot of loss associated with that, and it's a big deal in power transformers because you go round this loop every electrical cycle. So if you're running at 50 hertz, whatever energy is associated with that is happening 50 times a second. If you're doing it in a ferrite switch mode transformer, that's happening at 50 kilohertz or even 500 kilohertz, maybe even 5 megahertz these days. So hysteresis losses become very important in ferrites, and you have to choose your materials with considerable care. There's another thing, seeing as we're rambling beyond the scope of it, I didn't mention anything about skin effect and conductor losses in transformers. Skin effect, of course, is what happens if you take a long piece of wire, from one end of the garden to the other and pass high frequency current down it, and its resistance increases with frequency as the current diverts to the outside of the conductor, because of the magnetic fields that are induced within it. That gets worse. The point about skin effect gets worse as you wind the coil up into a tight bundle in a transformer, because not only do those conductors have their own self-induced magnetic field in them, they've got field from all the other blooming conductors that are next to them. And so you get induced losses in the bulk of the conductors, and it's sometimes called proximity effect. And it's a very big deal in things like power transformers. If you wind a large high frequency power transformer with ordinary copper wire, believe me, to borrow another phrase the author knows, things get very, very hot very quickly, because not only is there skin effect, but there's this thing called proximity effect. It's seldom an issue in audio transformers because, one, we're not running at very high frequencies, and two, we're tending to wind, because we're using low frequencies, we're winding large numbers of turns of thin wire. So the skin effect and the proximity losses are not a big deal. But if you're building switch mode power supply transformers for anything but other than piddling power, you will see things like Litz wire being used, where you've got lots of individual insulated enamel conductors twisted together, woven together in a very specific pattern. And the design of those types of transformers really is a specialized business. There's a company, I think they're in Spain or Italy, forget which, I think it's Spain, called Frenetic, who make a living basically designing transformers with the right number of strands of eddy current mitigating Litz wire, as it's called, Litzendraht, German word. So yeah, there is more, but the art of being boring consists, as somebody once said, of trying to say everything. And I think I've probably gone far enough down that road tonight.
Okay, thank you everyone for attending. Thank you, Mike, for a fascinating presentation.
You're very welcome. Thank you.
Yeah, it's good to learn about these things. Thank you, everyone. Take care.
Thank you, Jamie. It's old stuff, but it needs remembering. Bye-bye, everybody. Thank you.